Okay, well, I'm at the airport, so every once in a while you might hear some beep, 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 or some announcement about a flight or something like that. Or you might hear dot, dot, dot or something. Anyway, so we want to look at separation of variables for differential equations. So separation of variables. And in this first part, I just want to look at why it works, or what's going on that it works. And so let's take a relatively simple differential equation like y prime equals, let's say 2yx. And so if I want to try to solve this differential equation, one way to do it is to try to get it so that we just have a function of y times y prime, and then have that equal to something just involving x. But it has to be times over on the left hand side. So in this case, if I divide both sides by y, I get y prime over y equals 2x. And this satisfies what we need, because you see we have 1 over y times y prime, and on the other side we just have a function of x, 2x. So we have done what it is we want to do, and we separate this thing. Now I simply integrate with respect to x, and that's the important part, and we'll see sort of where the shortcut stuff comes from that people tend to do. But you know, when you think about it, see, I have a function of x on the right side. That's a function of x. But we're assuming that y is a function of x. And so on the left side, this is also a function of x, because y prime is a function of x if y is a function of x, and we've got y is a function of x, and so one function of x divided by another function of x, or if we look over here and think of it as multiplication, one function of x here times another function of x is a function of x. And so both sides are functions of x's, and therefore that means we could integrate both sides, and at least up to an arbitrary constant we should get the same answer. So if I integrate y prime over y dx equals the antiderivative of 2x dx. Now, as long as I've got my integral signs, I'm not going to worry about an arbitrary constant. But these antiderivatives could differ by an arbitrary constant, and so we'll try to remember to put that in every time. But now, so the right-hand side is a piece of cake. I can do that. I get x squared over there. The left-hand side, on the other hand, I don't know, you know, we have to think about how we do that. Well, we realize that we actually can make a quick substitution here, and that is that we've got y prime dx. And if you remember from Calculus 1, and even if you don't remember from Calculus 1, it's still true, that in terms of differentials, the definition of dy is y prime dx. And so that's exactly what we have up here. So this left-hand side we actually can write as dy over dx. Sorry, try that again. We can write it as dy over y. And then the left-hand side is still the antiderivative 2x dx. Well, now I can do...
Information booth paging, Joseph Black. Joseph Black, please meet your party at the information booth, lower level.
Okay, any of you seen Joseph Black? If you have, let him know he needs to go to the information level. So anyway, we have this antiderivative dy over y and the antiderivative 2x dx. Now 1 over y, the antiderivative of that is natural log. Now this is very important. It's the natural log of the absolute value of y. And then equals x squared. Now, one of these two sides, we need to put an arbitrary constant. It typically is done on the x side because we're trying to solve for y if we can. So what we have now is that the natural log of the absolute value of y is equal to x squared plus c. So there we've solved it. We have, at least in this case, an implicit representation, okay, of y in x. So it's implicit because we haven't explicitly solved for y. Now we can do that. We can exponentiate both sides, and if we exponentiate the left side, we just get the absolute value of y, and if we exponentiate the right side, we get e to the x squared plus c. Okay, and now at this point, this is where, notice the absolute value matters a lot. A lot would come from our initial condition. So if we had an initial condition that said, say, y of 0 was -1, well, notice that when we take the absolute value, we would drop that negative, and over here we've got e to the x squared plus c. Well, e to anything is always a positive number, and so that's where you have to be very, very careful about these absolute values, because without any information like this, so let's scratch out that information, then what I know is y is either plus or minus e to the x squared plus c. So that's what I know. Whoops, I don't know why that was moving on its own, but and so with that, we would have to be very careful. So whenever you get these absolute values involved, just be very careful, and we don't really know what the answer is unless we get some initial condition. But I'm not going to go into that now. Right now I'm just interested in sort of why this separation of variables up here works. And again, how it worked was by separating the variables into a function of y times y prime, and then a function of x on the right-hand side. When we integrate both sides with respect to x, we get to make this substitution. And so because of that, we're able to, at least as long as we're able to do the antiderivatives on both sides, which we were in this case, we're able to get further along in our solution. And now, once you get that solution, anytime you do this, you may still end up and get stuck at the implicit part. You may not know how to solve for y, but in this case we did. Now the same problem, the way you typically see somebody do it when they're just kind of doing a homework exercise or something like that, is if you have y prime equals 2xy, I think, or 2yx, whatever I wrote, what you tend to see them do is they'll just write it like this. They'll say y prime over y equals 2x, and then all of a sudden the next step, what you'll see is the natural log of the absolute value. Well, if they do it correctly anyway, you'll see on the next step the natural log of the absolute value of y is x squared plus c. So you see they'll just mask this substitution part, this integration of both sides by x, and this substitution dy. And that's okay. I mean, there's absolutely nothing wrong with that. I tend to do that myself. If you do this enough, it becomes just a mechanical thing. But it would be nice if you remember that the only reason you get from here to here is because you did an integration with respect to x, and because the function of y here is multiplied, and it's 1 over y, so it's multiplied times the derivative of y. That's why when we integrate both sides with respect to x, we can make that substitution. Otherwise, we could still do that sort of substitution, but it wouldn't really get us anywhere. We would have a problem with that, and so you really want this to be a multiplication here, times y prime. If you end up with a subtraction out here that doesn't have a y prime in it, that integration no longer works. And that's I guess the best reason for putting that step in, but honestly, you usually don't see that step done. And so you just go from this step here to this step here as a second step when you do that separation of variables. So that's the idea of separation of variables, and that's all there is to it. You just need to get all the y's on the left, all the x's on the right, but it's very important that on the left, y prime is multiplying everything that's on the left. And you could have constants on the left, but typically you wouldn't worry about it. If you've just got constants, you'd leave them on the right. And so you just want to make sure that y prime multiplies everything on the left. Notice I said everything 3 times because it is very, very important. Okay, so that is sort of how it works, why it works, and so that's what we'll do for that video.